So, very good morning to everyone. My name is George Zubelli from IMPA, and it's really my pleasure to introduce to you today Professor Diogo Gomes. Diogo Gomes graduated from Berkeley. I actually met him while he was still a graduate student in 2000, and he's now professor at KAUST in Saudi Arabia, and I was very happy to know that he has been doing very, very interesting things on the fields of PDEs and regularity for mean field games. And I met him scientifically for the first time in a very interesting meeting back in Yerevan with a very good group of people. And I was impressed at that point already for his work. So thank you very much, Joe, for being here.
Thank you so much for the kind invitation. I always love to be in Rio, and this is always a great pleasure to talk here in this room. So today I'll be talking about mean field games and some of the work that we've been doing in my research group. And what I decided to do is to have about half of my talk to be an introduction to mean field games in the continuous setting, and then in the second part I'll discuss finite state mean field games and what can be done numerically with them, and why this is a useful thing for also continuous state mean field games. So what are mean field games? Well, these are models that describe large populations of rational agents which compete, and they seek to maximize or minimize some utility function. And these models described a lot of problems in social sciences, economy, biology, and so on. They were introduced about 10 years ago, more or less at the same time in the engineering and mathematics community by Pierre Lyons and Jean-Michel Lazry and Peter Keynes and his co-workers. And they actually fit something that I like to call the measure potential framework. And honestly, measure potential framework is what half of the people in this room, or probably more, do. So probably this slide is unnecessary, just the name is a bit different. But what we are doing is we have a system with a very large number of agents, and the way we describe this system is by a probability density, which gives us the distribution of the agents somewhere in a state space. Then agents interact with themselves, and somehow these interactions are encoded in a value function or pressure, like in Jan's talk, or maybe some convolution of M with some kernel, like the talk yesterday by Lisa, which encodes the effects on the environment. And given M, given U, well, U is given by a PDE that depends on M, and somehow solution drives the evolution. And this, as I told you, arises in crowd, chemotaxis, economic growth, price formation, traffic, energy systems, and many more that I'm probably forgetting right now. Because what is common in all these problems is that they involve very large number of agents which are either rational, let's say in economics, or maybe due to evolutionary pressure, only survive if they are rational or act rationally. They may not think, but actually their actions may be somewhat rational. Now, mean field games comprise typically two systems of equations. One is a Hamilton-Jacobi equation. The other one is a Fokker-Planck or transport equation. They are coupled in some canonical way. Now, because I think that some of you may not be familiar with Hamilton-Jacobi equations, or I'll actually go through a very quick derivation of this model and explain where they come from. And if you are familiar, I've been told that you can never underestimate how much people enjoy hearing things that they actually understand. So if you don't enjoy, I apologize in advance. Now, I talk in the title about monotonicity. Monotonicity is crowd aversion. I mean, in this setup, really, what monotonicity properties in mean-field games encode is crowd aversion. And crowd aversion has a number of consequences. For example, if I tell people in this room that you guys love crowds and act accordingly, well, you'll just pile up somewhere, right? And there are many, many places where people can make a gigantic human ball and pile up. But if I tell you, well, you guys are crowd averse, act accordingly and move around this room freely, then there is essentially only one way. I mean, you try to keep other people at arm's length and spread uniformly. So up to permutations of the agents, once you are crowd averse, there are a number of consequences. And the consequences can be seen as uniqueness or can be seen as regularity, because you have a uniform density instead of Dirac delta somewhere. And this is what we'll see in this talk in some examples. So, quick crash course on optimal control. So the setting of optimal control, recall that we have agents, they are rational, they seek to minimize something, and the simplest way is to say, well, we have here? No, doesn't point. Okay, got it. Sorry. So you fix Lagrangian, which is the cost of moving if you are at state x and move at speed v, for example. You take a terminal cost, the cost that you pay at the end, and what you want to do is to minimize the running cost plus the terminal cost. In this setting of optimal control, you always look at terminal costs. And the reason is very simple. If I tell you that, I have an enforcer somewhere in the room and you need to pay me 100 reals now, that's it. I mean, you guys pay up. But if I tell you, well, there is an enforcer in the room, and if you are around by the end of this talk, you need to pay me 100 reals, then, maybe people can act upon that and quickly leave, or maybe leave 5 minutes or 30 seconds before the end. So if you have current costs, you need to pay them, at least if they are enforceable, but future costs, terminal costs, can be optimized. And so this is the setup with these equations. And of course, what we would like to know is, well, can we characterize the value function? Can we compute optimal trajectories? Does the value function u gives me something about the optimal trajectory? And the answer is yes, kind of. So what you do is that you build something called the Hamiltonian, which is the Legendre transform of the Lagrangian. And it turns out that if the value function is smooth, then it solves a Hamilton-Jacobi equation, which is the first-order partial differential equations, together with some terminal condition, which is the terminal cost, naturally. Now, in general, if you are familiar with PDEs, you know that first-order equations do not have classical solutions, but they have something called viscosity solutions that are almost as good as classical solutions. This theorem is actually used a lot by engineers. It's something called the verification theorem. So sometimes you give me a Hamilton-Jacobi equation, and you can solve it. I know that I just told you that in general, first-order equations do not have solutions, but sometimes they do. Sometimes the terminal cost is quadratic. Everything that shows up in the equation is quadratic. You end up with a Riccati equation. You solve it, and you get a solution. And if you get a solution, a classical solution, then it's not hard to prove under convexity assumptions that the solution to the equation is the value function, and the trajectories are given in feedback forms. And you can see feedback form. And you can see why people doing applications like this, because you solve the Hamilton-Jacobi equation, then you characterize the optimal trajectories based only on state and time. So instead of having to minimize among all curves, you say, well, if I'm point x at time t, this is the direction in which I move. Now, if you are just one person, if you are more than one person, moving according to a vector field, so following a vector field, you can ask the question what vector fields do if they are, or what probability densities do if they are transported by vector fields. So if you have an ODE, you can consider the flow, which is just a map that takes initial conditions to time t. And then you define something called the push forward, which is just the probability measure defined by taking the agents at time x, seeing where they're averaging with respect to the initial conditions, the function at the position at time t. And what it turns out is that M defined this way, by the Reason representation theorem, M is a probability measure, is a weak solution to the transport equation. It's actually a classical solution under enough regularity. And in particular, if you are following some optimal control trajectory, well, then you have this equation that depends on you. So if you have a single agent, computes a value function. Given the value function, you have multiple agents, all with the same cost, doing the same thing. They follow transport equation. The thing in mean field games is that the Lagrangian depends on M itself. And if you know M, well, then it's kind of clear that you should solve the Hamilton-Jacobi equation. And if you know the solution to the Hamilton-Jacobi equation, to know M, you should solve the transport equation. The problem here is that U has terminal conditions, and distributions is known in the beginning. Distribution of population is known in the beginning. So this is really a fixed point problem. It's just that you go forward with one thing and you come back with some other thing, and they need to match. Because in general, this Hamiltonian depends on U, X, and M. So you need to know U to evolve here, and you need to know M to evolve there. And it's not even obvious whether you can have solutions, because these things need to match properly. So the questions that we are interested in, are general questions that people may be interested in, are, well, can we characterize uniqueness, for example? Can we solve explicit examples? Can we understand what's going on? Can we prove existence? And can we develop effective numerical methods, as these equations tend to be kind of messy and really analytical solutions will be sparse. Although I'll show you some neat examples that we have. So let me tell you the kind of things that we are looking at. I mean, the kind of general mathematical difficulties and why we care about them. Well, typically you want to look at costs that look somewhat like this. And somewhat like this means the following. If you move fast, it's expensive. Okay? This is also convex. So if you sprint and you walk, it's actually better to go at a nice jog. So convexity, this is basically what it means. Is in terms of velocity, is that it's better to jog than to walk and sprint. Maybe, depending on alpha, if you go across a high-density region, it's very tough to go across a high-density region. Maybe there are some places that you like, and maybe you look at the other agents, and there are areas with high density or low density that you prefer to be. So one thing is about moving, the other one is about being. And now this becomes a bit of a zoo. And I need to tell you this because otherwise you don't appreciate so much some of the results that I'll show you. It's that all of these equations look the same, except for technical reasons. They really tend to have different treatments. For example, if you have alpha greater than 0, you have congestion. Congestion creates denominators in the Hamiltonian, makes the equation singular when m equals 0. This looks more like a technical issue because really congestion should be about high density, not about low density. But well, low density is the thing that shows up and really creates problems in the equation. Large gamma or small gamma creates different issues because you have different growths in the equation. And then you can have a number of things. For example, you can have non-local effects. You look at an average, and if it's high density, you like it. If it's low density, you don't like it. Maybe you don't like high density regions, but you're kind of neutral about zero density. Maybe you don't like high densities, but you love empty places because the cost is minus infinity. Or really, you don't care about high density, but you really love empty places. And there are a number of interesting effects. For example, in this last case, if you love empty places and everyone loves empty places, there are no empty places because they get filled. And this is something that you can actually prove. So what kind of things do we want to do? So we want to address two things, mostly today the stationary problem. So this is the system that we want to solve. I mean, you need to add some additional constant h bar for solvability. For example, if the Hamiltonian is strictly positive, there is no way you are going to have a solution with 0 on the right-hand side. So there are some solvability issues that need to be taken care of. So really a stationary solution is something plus h bar t is a solution. And this is kind of clear once you start playing with a bit of examples. Or the time-dependent problem. You can also add Laplacians. You can have second-order effects which correspond to noise. And each of these problems somehow has its own techniques. Now, it turns out that really one of the few things that it's common about this class of problems is that monotone operators show up in all of them. And let me recall what a monotone operator is. My favorite Hilbert space is R. And a monotone operator in R is an increasing function. Okay? In RD, that's my second favorite Hilbert space, the gradient of a convex function is a monotone operator. There are monotone operators which are not gradients of convex functions. And in general, this is the definition of a monotone operator. If you think about R, you take a low value, high value, low value, high value, and you have an inequality. Okay, and this goes in the right direction if this is an increasing function.
Do you really need Hilbert? Can you go to Benoit? Why?
You need some kind of duality. Yeah. I mean, actually, we will work with distributions and with D and D prime. So a variational inequality is the problem of finding a W such that this inequality holds for every Z. Now, why would someone care about that? Well, because if A of W is 0, it satisfies the variational inequality. So solution of A of W is 0 satisfies the variational inequality. And it turns out that this is a much more robust object if you are working with monotone operators. So sometimes you may not be able to find solutions of A of W is 0, but you may be able to find objects like this. And if you do optimization, you have done this. If you minimize the function x squared, you get x equals 0. But if you minimize the function x squared in the interval 2, 4, you get x equals 2. And if you look at what it is, well, you're actually kind of finding a point where the gradient is 0 between 2 and 4, but really such thing doesn't exist for the function x squared. And this is called the KKT conditions, I guess, in the setting of optimization. So if you look at stationary mean field games, for example, what it's interesting is that the equations that we had before correspond to a monotone operator. So if you write down the monotonicity condition in L2, and I'll spare you the details. By the way, it's not hard. It's just a bunch of simple computations. You take this at one point minus this at another point. multiply and go. Now, one thing that's interesting is that actually the order of the variables is this one. So you should think of the first equation as kind of the equation for M and not for U. I mean, typically you look at the Hamilton-Jacobi equation as the equation that determines the value function. In this setup, it's actually the equation that determines M, and in some sense, the equation for M, the transport equation that usually you think about an equation for M, should be thought of as an equation for U. And this has some consequences in the way we work with this. Same thing for time-dependent mean-field games. So you also have, under initial terminal conditions, you also have a monotone operator popping up. Now, why is monotonicity good? Well, this was already observed by Lazare and Lyons. They really didn't talk about monotone operators, but it's really what it is that often monotonicity gives uniqueness. So if you are looking at solutions of A of mu is 0, and you have two of them. Well, if you have two of them, then this is 0, so of course this identity is 0. And monotonicity tells that the same thing is greater or equal than 0. And now if you can make it just a little bit more strict, then you have a contradiction. How does this work with mean-field games? Well, the simplest example is this time-dependent case where you write this expression, and what you get is this integral identity. And you will stare at this integral identity and you say, well, if I have two solutions, then M must be equal to M tilde. Maybe they are 0 somewhere, so really you cannot make a statement about the gradients, because maybe they are 0 in the set where the gradients are different, but clearly M should be M tilde. And then you look at the Hamilton-Jacobi equation, you say, but the Hamilton-Jacobi equation has uniqueness of solution, so U is in fact unique. Now, the other thing that I want to address is smoothness. Smoothness and existence of solutions. If you stare at this system for a while, and you're used to this, you know that in general, Hamilton-Jacobi equations have at best Lipschitz solutions. And the expected a priori type of bounds for Hamilton-Jacobi equations, the Lipschitz may be semi-concave if you know something about M. I say, good. Now let's go to the transport equation. What can we say about the transport equation if you have bounded vector field? Well, actually very little. I mean, you can say that M is a measure. But if M is a measure and you plug it in the logarithm, then you are going to have problems somewhere. So it's actually quite surprising that this equation has smooth solutions, as was proven by Evans in a different setup. He was not looking at mean-field games, but it turns out that this problem has. But this is not the general situation. Even simple mean-field games like this one, where you really have a linear nonlinearity, may fail to have smooth solutions. And this is actually quite easy, because what you do is that you can solve this equation, and you get the formula for M. And then H bar is determined by the normalization condition. Okay. You go through a little bit of algebra, and then you try to plot what happens as lambda increases. And for small lambda, everything is fine. The density is nice and smooth. But once lambda hits a threshold, then M gets regions where M is 0, and you no longer have a smooth solution. So this is a numerical rendition of an exact solution. Now, the reason why we could actually solve this is because this is monotone in M. And let me explain a little bit what is the general principle to get this type of solutions. When we look at this equation, stare at the second equation and say, well, this guy is constant because its derivative is 0. So let's call it J. And let's consider the case J different from 0. You look at this, you solve for Ux, and you replace in the first equation. Now you have an algebraic equation for M. Oh, this is fantastic, because we had a PDE, and now we have an algebraic equation. And if you look at this plot, because the first function is decreasing, the first function is decreasing, this function here is increasing, so minus is decreasing. This is a globally decreasing function. And so there is at most one value of m for each value of h bar and x. So you have a unique solution. Once you go to the non-monotone case, once you have the lack of monotonicity, then what happens is that this function is decreasing, but this other function becomes increasing. And now, for each value of the right-hand side, you have two possible values for m. And you glue these things together. And what I'm doing here is plotting solutions with different current levels. So each frame is a stationary solution for some j. And you have very interesting effects. And you have seen this. You have been there. You have been to a museum. I like the museum. Because you enter the museum, and everyone goes walking quite fast. And then you see a lot of people, right? You see a lot of people, and then you stop, because certainly there should be something interesting there. It's just the restroom line. Okay? If you look at what's happening here, and this is usually not a desirable place to be in a museum. If you look at the solutions they are doing exactly this. So they are low density, then they arrive to an undesirable region, but because there is a lot of people there, people just stop because they also like to be with people. And the combination of undesirability, which is encoded in V, and having more people, which is encoded in the M term, combined, gives that this is actually a good place to stop and stare. Now, once you understand this effect, you realize that this thing can happen in multiple ways. We like to call this thing unhappiness traps. So here we have a potential, which is bad in the middle. I mean, the way to see this is that middle is bad. You don't like it. And let me pass it again. And now, each frame is a stationary solution. On the left, you have M. On the right, you have U. And the curious thing is that there are these solutions where people get stuck in the middle where they don't like it. And you probably have done this too. You probably went to the place where your friends are, and you really don't like it. No one really likes, but it's where everyone goes. And because you have this balance of desirability, which is encoded in the potential, and just having a bunch of people, and this is a stationary situation, then you have multiple solutions, multiple equilibrium configurations. And you have lack of uniqueness of solutions also. So this is another example where you have multiple solutions for the same current. Now, so whenever you have non-monotone mean field games, you have fairly pathological behaviors. One of them is this unhappiness traps, where people get trapped with their friends in undesirable places. Now, fortunately, these things are unstable by adding viscosity. So if you have a monotone mean field game and you add a little bit of viscosity, then you stay more or less the same. But if you have a non-monotone mean field game and you add viscosity, then people stabilize and they actually go to the ends. Recall that in this case, this is undesirable, this is desirable. So you have this equilibrium configuration with no viscosity. Once you add a little bit of noise, then these things go. So maybe in the time dependent, there will be nice effects like metastability and so on as you look at this. Now, what about solutions? So as I said, a zero of a monotone operator is always a solution to the variational inequality. And if the domain is large enough, then you can go back, and the operator is relatively nice. the other way around, it's not true in general. So if you have an operator which has a domain that's not very large and so on. Now, it turns out that there is something called the weak solution to variational inequality, which is this concept. You see, this looks precisely what I had before, but it's not. So here, W is a solution if A of W, Z minus W is greater or equal than 0. And it's very easy to see that if A of W is 0, then this, of course, is 0. You think a little bit, and you can go back if A is what is called Hammett continuous. Now, weak solutions are much more interesting objects because A of W never shows up in the definition. It's only A of Z. So it turns out that there is an obvious implication, solution to the variational inequality, weak solutions. And sometimes you can go back. Let me give you an example. You take a continuous function, and you want to solve A of Z equals 0. And now the statement is that A of 0 is 0 if and only if A of Z times Z is greater or equal than 0 for every Z. Because A of Z is positive or greater or equal than 0 for Z greater than 0, is negative for Z, or negative or 0 for Z less or equal than 0, and by the mean value theorem at 0 has to be 0. I mean, it could be flat, but as long as it's continuous, this is fine. So you see, this is a way to define that something is 0 without ever writing A of 0, without computing the thing at the solution. And this is something that people in PDE use all the time. When you do weak solutions and you integrate by parts, let's say weak solutions for the Laplacian, and you integrate by parts, what you want to do is to define a solution without ever writing Laplacian of U. Why? Well, because you actually don't know whether you can write Laplacian of U, but maybe you can come up with a definition that's independent of the Laplacian of U, and maybe later on you can prove it. So if you go back to our mean field game, the original thing that I showed you before, we can define weak solutions exactly in this manner. So we say that the pair M and U is a weak solution if, well, the previous inequality holds. The good thing is that eta and V are test functions. So you never compute A of M and U. So this means that you can look at weak solutions as very weird objects. For example, distributions. U is a distribution and M is a distribution. Well, maybe M is a positive distribution, hence a measure, but U could be a distribution in principle. So now we want to know whether we actually have solutions to this problem. And we do. So this is something that I proved with Rita. In general, we have solutions, and they are a bit better than just distributions. They are actually, M is a measure, and U belongs to W and gamma. And this is a technique that gives you solutions pretty much for every monotone mean field game in which you can prove a priori estimates. So really the trick here is that you need to be able to prove some kind of a priori estimates. Then you use something called the Mintis method to pass to the limit and get the solutions. Now you can actually do a little bit more. You see, I rewrote here the definition of weak solution. And what you'd like to do is to prove a little bit more regularity. And in fact, what you can show is that the Hamilton-Jacobi equation is the subsolution. So use the subsolution to the Hamilton-Jacobi equation in D prime. M solves the transport equation almost everywhere and as a distribution. And in particular, in the set where M is positive, so where there are agents, you actually solve the Hamilton-Jacobi equation. Recall that this is what we want to look at. And what we get is that the first equation holds, the second equation holds almost everywhere, which is pretty good. U is a subsolution, so you have an inequality. And where there are agents, you actually have a solution. So this is the setup. Now, what more? Well, actually, once you start realizing that these monotone operators are useful, you start trying to use them in a lot of things. And one very simple observation is that if you have a monotone operator, and every time I talk about monotone operators, if it's in general, think about increasing functions in R. And this will simplify understanding most statements. In this case, so if you take a monotone operator and consider this flow, this is a contraction. Think of W dot equals minus W. This is a contraction in R. And now this means that we can use this thing to build numerical methods. So for example, if we take this mean field game, so we want to solve this thing equals to 0, you take two solutions, then what happens is that the L2 norm between any two solutions contracts, and in the limit you get a solution, provided the solution stays positive. And I'll say a little bit more about that. And once you run this in examples, you get very fast convergence to solutions, because this is pretty much an exponential contraction. So you get a lot of, and this works, for example, as a numerical method, works for congestion problems, works for two-dimensional problems, where you start with some arbitrary M and arbitrary U. You flow through this monotone flow, and what you get is, in the limit, and usually the limit is in a short time, a stationary solution. Let me go back and tell you just a small remark. The interesting thing here is that this flow is really weird once you start looking at it. I mean, this really looks like a Hamilton-Jacobi equation, except that if you start saying, well, you put the M and the U in the wrong places. No, I didn't. This is the correct thing. So you are evolving M with the Hamilton-Jacobi equation, and they are evolving U with the transport equation. And why would someone do that? Well, there are two answers to this. One is that this is a monotone operator, so this contracts. The second is that you try everything, and eventually you figure this out, and a posteriori you find that this is a monotone operator. But actually, there is a good reason to do this. And somehow, the explanation of this method is the following. Suppose I give you some distribution of M and some tentative cost. Okay, I give you some M, some tentative cost. And I say, well, how should I improve this so that I get closer to an equilibrium? Well, you see, if it's expensive, you should reduce M there, because people probably don't want to be in expensive places. And this is what the first equation does. So the first equation is basically doing the following thing. Looks at the cost of being in a certain place. And if the cost is high, reduces M. If the cost is low, increases M. This is why you have the Hamiltonian. You see, the Hamiltonian is related to the Lagrangian, to the cost, and this is roughly the explanation. Here is this, if the cost is low, if people are coming in, this is what the divergence of MUX tells you, that when people are coming in or going out. But if people are coming in, it means that it's too cheap, so it makes it more expensive, so that people don't come in. So somehow this algorithm, which has a nice interpretation in terms of monotone operators, is most likely the kind of thing that you would do if you try to do this thing by hand, right? I mean, you have a distribution of people, and then you want to avoid people to go to the expensive places, so you decrease the density, and you try to adjust things in such a way that you get an equilibrium in the end. Now, what about real numerics? Well, in real numerics, you actually need to discretize this Hamilton-Jacobi equations, which we did here. And what you end up, in fact, is with something that I studied many years ago for other things, which are finite state mean field game. So once you write a discrete version of these operators, or the time-dependent problems, and you stare at them for a while, what you realize is that you actually have something called a finite state mean field game, where agents, instead of moving in a continuous fashion, they hop from place to place. Okay? And so they have these discrete hops. And of course, because we are mathematicians, we can consider two-point discretization of Hamilton-Jacobi equations. This will be our running example here. But I really want to understand what this thing is, with finite state mean field games gives us. So we start looking at the numerical perspective on this with a student of mine, João Saúde. So basically, you have finitely many states, these states, and players can control the switching rate from one state to the other. So the state of this game is given by a trajectory of probability measures on the simplex, the d-dimensional simplex. And you have an initial distribution of players. Player seeks to minimize a given cost. And I'm not going to write because the notation here is much, much more cumbersome. So I'll skip a little bit on the notation. So they minimize a given cost that depends on their state, depends on theta, the other player distribution, and depends on their switching rate, plus a terminal cost. Like in the deterministic case, except that now the dynamics is not deterministic, it's a random process. And each coordinate of the value function is just the cost of the player located at state I. Now, as before, you can build a Hamiltonian. Out of the Hamiltonian, remember that the optimal trajectory was dph. Here you have some switching rate that comes from this Hamiltonian. And you end up with a system of equations which is really a discretization of the Hamilton-Jacobi equation. So if you put the capital H here and put some divergence, this is the forward Fokker-Planck equation in discrete time. This is really what this guy is. And now we are interested in understanding this problem, and because here we are talking about ODEs, not PDEs, all the functional analysis is pretty much gone. Actually, it's not true. Some functional analysis still remains, and you'll see it. So a model, in addition to things that come from discretizing continuous state mean field games, there are a number of models, and the paradigm shift problem is exactly one of this, where you have a cost that depends on the intensity of the switching rates, plus some cost which at state I depends on the number of people working in state I. So you can imagine the situation where people want to work. Actually, here in these problems, for some reason, in my original paper, we put things to maximize. So here you want to maximize your work in the area where more people are working, for example, and I want to see how these things switch. So the costs are not costs, so you want to maximize the time that is spent in the state which has more people. And you see now, once we write what the Hamiltonians for this system are, you realize that they are pretty nasty. I mean, these things are not very complicated, but this is the simplest problem that I really can come up with. And really, this is the kind of equations that you end up. So there is no way you can solve slightly more complex problems than this one without going through numerics and without at least trying to understand qualitative features of these problems in terms of monotonicity properties, in terms of general conserved quantities, and so on. This is the positive part. So this is really nasty for formulas. And if you try to solve equations that switch from one regime to the other with things like positive parts, then they are not so nice. Now, but the same features are here, which is that we have terminal costs for u, the value function, initial distribution for theta. So theta and ut are given. I want to look at this system of ODEs and produce ways to solve this system of ODEs. Now, as before, we have some monotonicity structure. And this is really what saves the day, what gives uniqueness of solution by the same reasoning as before. It's actually a bad idea to start like I did with finite state mean field games. So I started studying mean field games because I thought that this would be a much easier problem. It turns out to be a much messier problem in terms of notation. So less technicalities, but notation tends to be a lot heavy. Now, for stationary problems, we can do the same thing as before, which I explained, which is this, well, you take this operator. This is a monotone operator. So we just flow theta and u with this monotone operator. And I mean, as long as theta is properly normalized, so there is a constant, this is a contraction, and converges to a solution, to a stationary solution. And this is really what you see here. You have two states. You start with some random guys, and then very fast, this converges to stationary solution. The interesting thing here is that these things don't naturally approach. They actually do some crazy trajectories. So they actually increase in distance, and then they get together. And this is because it's not the difference between the probability measures that decreases in time. It's the difference between the probability measures and u squared. Now, once you look at this picture, you say, well, but couldn't this guy go above 1? Couldn't we have situations where you are on the probabilities and you get out of the probabilities by going above 1? Well, yes, this happens, and this is the case. Okay? This is the case. So sometimes if you just do this unmodified flow, what can happen is that you can get out of the probability measures. So some densities in these two-state problems will exceed 1, and the other ones can be negative. And in principle, it could even lose contraction. Now, it turns out that there is a fix for this, because if you have a monotone operator and you conjugate it with a projection, you actually get another monotone operator. And this is exactly what we did here. So this is again a contraction. So you can cut off these guys, and there is a canonical way to do this cutoff, in which you not only stay in the probability measures for all time, and you still have the contraction property. So this is possible. This is just projecting. This is nothing very special. Time dependent. Time dependent is a bit trickier. Why? Well, you look at this operator. Formally is a contraction, but actually there is some time integration. And really, in general, this flow does not preserve initial terminal boundary conditions. And this is something that you really want to go solve this equation and keep the boundary conditions fixed, because you want to solve a problem with initial terminal boundary conditions. You don't want to solve another problem. And this is where actually functional analysis helps us a little bit. So the idea is this. You look at the right-hand side of this operator and say, I have theta, right? So this is the transport equation. And I want to evolve u using this equation. So I want to keep the terminal data fixed. So what I do is that I use a bit of, well, this is really Rees representation theorem in a variational form. But what I do is that I try to minimize this integral with phi of t 0. So this is the orthogonal projection in H1 of this guy on the space which have terminal data 0. So this functional here represents, so the solution phi represents this linear functional as an inner product. You do, and this follows just from the Lagrange equations, or it's actually one of the standard proofs of the Rees representation theorem. So the idea is that you take this guy, you solve this ODE with phi of t to be 0. This is just an another boundary condition because you need two of them. So it's a natural boundary condition. Now, you define capital phi to be the solution of this equation with these boundary conditions. You play the same game with the other equation. And basically what you are doing is you have a monotone operator, and you are projecting one part in the zero boundary conditions at the end, and you are projecting the other part in the zero boundary conditions at the beginning. You do this, and you define this new monotone deformation flow, which instead of putting here the transport equation and putting here the Hamilton-Jacobi equation, you put their projections in the right boundary conditions. And what happens is that this is now a contraction not in L2 but in H1. And this preserves the boundary conditions just because these guys are zero where they should be at the beginning and at the end. So the idea here is that we are working in, we start with some curve, so this is time. There are two states, so maybe there are two curves of this. We introduce a new parameter, S, and we try to evolve this with respect to S. So we start with some arbitrary curve, and what we are doing is that evolving this thing in this new time and see what happens. Now, this is the exact solution in green. And this is one state, this is the other state. And this is what happens. So this is time, this is S. We start with the initial condition, then we evolve with this fake time, and very soon we get to the stationary solution. So this is theta 1, and this is the difference between the two guys. And pretty much you get the exact solution back. Now, you can play the same game with other examples, and you get, well, some other non-trivial solutions where. Now, same issues with positivity arise. So you need to take care of these positivity issues with a bit of care. Same trick with projection also works. Because the name of the game here is every time you have something that needs to be preserved, you can use projections, and projections behave well with monotone operators. And you see here in this last example the contraction of the H1 norm. It's really, really fast, and these guys could pretty much disappear very, very soon. So this would not be possible with a lot of people, and I'm listing here hopefully all my collaborators that were involved in this project and some related ones. So I think Rita next will be talking about a problem which was not covered here, but hopefully this was also an introduction to mean field games. So thank you very much.
Thank you very much.